code in F-star, day 13. Advent of Code is a set of programming challenges, one per day of Advent leading up to Christmas. It's run for several years now. I'm glad that my employer, Akita Software, is a sponsor of Advent of Code this year. You should check out the link to our jobs page on my channel. I will be using a language called F-star, which, as its webpage says, is a general purpose functional programming language. The thing that I like about it is it has dependent types. I don't use the effect stuff as much, although I use it some, but I mainly use the ability of dependent types to help us prove things about our program. So, with, let's be honest, limited success, because it usually takes me about 3 days to really get a proof in good shape in F-star, and there's always a new challenge the next day. So we're about 2 minutes away. I will get things set up since I have neglected to do that yet. I'll make a new directory. All my solutions are up on my GitHub page. I'm mgritter, M-G-R-I-T-T-E-R, and the repository is AOC F-star. I'll put that up a sec. So yeah, the warm-up problems I did from 2020 and the problems from this year are all up with some notes about the solution and what gave me trouble that day. Excuse me. So I edit in Emacs, which has a mode for F-star that does not exactly interactive proofs, but you can send things to the F-star type checker a statement at a time, and it tells you not always in great detail what went wrong, but whether it can successfully prove what you asserted at each step. I think there are some facilities for better interactive proofs, but I don't know how to make them work. And they don't seem to be documented. They're just a bunch of stuff in one of the F-star source trees. So. All right, here we go. Transparent paper is marked with random dots and includes instructions on how to fold it up. Which the first section is a list of dots. Okay, so coordinates. 0, 0 in the top left. The first value x. Yeah. Each fold indicates a line on the transparent paper and wants you to fold the paper up or left. Huh. Dots will never actually on a fold line. All right, that's convenient. All right. Part one is just the first fold. All right. What's our input look like? Lengthy. All right. So how are we going to represent? So the good news is we don't have to do a lot of folds, which makes sense because each fold, basically can expect it to have the size of the matrix. Do we want to represent all this as a matrix, or do we want to represent it as just a list of coordinates? I kind of like the idea of just representing it as a list of coordinates. I'm worried that in part two we might be asked to like print it out or something. There have been puzzles in previous years where like the dots spelled a message. But I think just a list will be fine. All right. So I'm gonna copy this input, and I think probably it'll be easiest to parse if we just split it into two files. How many are there? Yeah, there's like 900, which we could use as a literal, but we discovered on day one that long lists or long functions tend to cause problems. So let's, I think for the folds we won't bother parsing though, we'll just translate that directly. Okay, so we've parsed, have we parsed a list of coordinates already? Oops. Already this year? I don't know. All right, so let's define a record. I think we must have. What was day 5? That was 4 numbers. All right, let's copy that. We can use that as our starting point. All right. All right, that parses. Okay, so this takes a string, it splits it by comma, it maps this function, which parses it as an integer. There's not a function, unfortunately, to parse directly to the int type. We have to parse the machine size integer, but then we can just convert that. And this is just a standard map function. So we need, I think we're good there. And okay, so we're gonna parse the points in the order they appear in the file, although order shouldn't matter to us. And okay, so we're gonna need IO for read line. I'm gonna need the all module for the ML effect. That's what allows us to do IO. The default effect, an effect is a model of computation. The default effect is total functions, which do no IO, can't always terminate, return a value for everything in their domain, their inputs. All right, and then we're gonna do something. Probably what we'll do. All right, so what I'm thinking is we're gonna write a fold along X and a fold along Y function. Okay, so let's write it for a single point. So let me make sure I'm not getting X and Y backwards. So fold along X equals 5. Yeah. All right. So some ASCII art. So if we are less than X, no change. And if we're greater than X, then we move as far to the left of X as we were to the right of it. And we leave the Y unchanged. So this should be, all right, so if point.x is less than, or we'll say less than or equal to X, then return the point unchanged. Otherwise, return X is unchanged, and this is confusing. I'm going to call this the axis. So I think we have absolute value. I think I used that before. So this is the axis minus the absolute value of X minus the axis. And we calculate our distance this direction, and then we apply it, we subtract it from the axis. So if we're at +1, our distance is 1, we get a -1. All right. Let's, all right, we got a syntax error. Put a straight equals there. It should be p.x. All right. So let's prove something about this before we go any further. All right. So distance from axis is unchanged. So for any axis that's an integer and any point p, our lemma, which is the name for it's a helper function that verifies that something is true. It can take either precondition or postcondition. I think we only need one. So we're going to say the absolute value between absolute of ax minus p dot x. So the distance between us and the axis is the same if we fold the point along that axis. All right, and this is simple enough. Oh, fold dot x. This is simple enough. F-star can just send our definition down to the solver it uses, which is called Z3. It's a SMT solver, which stands for something that's equally unenlightening, but it knows how to do math, and this math is simple enough. It says, sure, that's true. Your function obeys the property that you said it did. So good. So let's write a similar version for y. Okay. So now we want to apply that to a whole list and along the way remove any duplicates. So the easiest way to do that, I think, is keep a set of, we may not even need to import that, is to keep a set of which ones have we seen already. So I want to write this so I can apply it to either version of this. So what we'll do is we will take a fold function, which goes from points to points, and a list of points, and return a new list of points. But to deduplicate, we need a set of points we've already seen. So I'll call it visited, kind of like yesterday, although that's not great. All right, this can be a recursive function. All right. Yeah, it should work. All right, so whenever we're doing recursion on a list, we handle the two cases. Either the list is empty or it isn't. So if it's empty, then return an empty list. Otherwise, so let's, our new point is what we get when we apply the fold function to the head of the list. And so if it's already in our visited set, so if, which order does this go? It says member first, then, okay, so if new point is in visited, then we just recurse without doing anything. So we call fold points with the same function, tail, and the same visited set. Otherwise, we're going to put the new point at the head of the list, which is not nice and tail recursive, but I think we can live with it. So, and we want to add it to visited so we don't see it again. And the way to do that is create a singleton with full points and take the union of that. Oh, no, the new point. All right. Let's, okay, so let's do the example fold first. How did he give us the, all right. So we need to do these in the opposite order. Let's write a function to do that. So here we'll take a list of fold functions. And apply them in order. So if we ran out of folds, then we just return L. Otherwise, we call that fold function. Okay. Do the rest of them on the result. I keep typing points instead of singular point. Warning, SMT, this is a new one. SMT may not be able to prove the type of folds. Huh. So because it's a list of, don't know why that would cause a problem. All right. I mean, it was a warning. It did manage to prove the function was well typed. So, all right. So then, example one is just a list of point to point folds, which we can give as a literal. So this will let us do it in order. So what did we call the functions along y7 and 5? So f star lets you query a function, so you can give the arguments one, just a prefix to the arguments and get a new function of the appropriate type, and that's what we did there. I'm getting tired of writing list point to point. I probably should give it a name, but and for now, I'm just gonna, as usual, I did not import the printf module. For now, I'm just gonna print the list. We might need to come back if I messed up and print out the list. Unfortunately, FStar doesn't, I think, come with an easy way to do that. So we want list.tote.length as the result. All right, let's copy over this example and see what happens. All right, real good. I. What am I missing? Oh, didn't give it the second argument, so it didn't actually give the result. It just said, okay, you can. It queried the function. All right. There we go. One, two, three, four, 5, 6, 16. All right. So what we were asked is how many are after the first fold. So what was in our fold along x equals 655? All right, let's see if that works. Plausible. All right. Yeah. All right. So we're gonna have to print them out. Phooey. All right. Sarah, let's just switch to. All right, we can do this. It's not too bad. We'll just put them all in a set and then iterate through the set. All right. All right, let's finish translating the instructions. All right. Y X 327 Y 223 X 163 Y 111 X 80 X 81. Okay, well we know the height and we know the width. So results will have height 6 and width 40. Although the last one of those should be empty, but I think we're good. All right. All right, so what we want to do is print matrix. I'll give the width, the height first, and then the width, and then result. Okay, which will work for the smaller example too. All right. We don't even have to put them in a set. We could just, there are only what, 240 elements in the set, so we just check them all one at a time. Sure. Let's be lazy and do that. All right. So y int and x is an int and max y is an int and max x is an int. All right. So if how do we want to do this? Let's print first and bounds check when we're incrementing. All right. So if xy is a member of L, then print sure we'll do it their way. Okay. So if x equals max x, then we need to print the end of the line. It should be print string. And go on to the next row unless that is too big. So if y equals max y as well, then we're done. Just return the unit value. Otherwise, y goes to 1, x goes to 0, everything else is unchanged. Okay, otherwise we just advance x. Pretty good. Oh, we need to make that into a point. All right, so it's going to be x equals x, y equals, is that right, or is it? Yeah, it is semicolon. What is on today? Folding points. And unfortunately for us, displaying the output, which I think I've just finished. So let's see what that does. Well, doesn't look so good for part 2. Why should it be completely blank? All right. I guess we better. But guess we better write the code to print out our list. Uh, oh, we can do this. No, because it's not a pair; it's a record. All right. Point string. There we go. Well, that isn't right at all. How did we? How do we solve the first point while getting this so badly incorrect? Oh. We didn't switch to part two. All right. Part one only asked us to do one fold, and writing a lot of GUI that I don't fully remember. What do you mean by that? Um, oh. Okay. Well, that doesn't look so good. Wow, we really messed something. I really messed something up in part one that did not manage to give me the wrong answer. I've got these negative coordinates. They're all in the y. Oh, well, I guess it may be that I didn't copy the input correct too. So let's double check that. X655, Y447. All right, that's better. 327, 223, 163, 1. It's the downside of not writing a parser. Is you're vulnerable to copying errors. All right, let's try that. No, still not right. X. Oh, I didn't save it. That would help. Okay, that looks sensible. Oops. LGHEGUEJ. All right. How did we do today? Pretty good. Not quite as fast as yesterday. I mean, faster than yesterday, but not relatively slower. Okay. Um, well, what? So, whenever I make a mistake here, I guess the question on my mind is always, you know, thank you. If the question is always, since this is a tool for proving correctness, what could I have done to make it work? And I guess the problem is I copied it badly, so that's not going to help. I don't think I don't recall errors. Maybe I'll have to rewind my own video to find out. Like we actually proved something out. Excuse me, about our fold function. Um, we could expand the specification of what fold along x does to say that p dot y is unchanged by this operation, and it can prove that too. So we can make the specification of what folding does a little more precise. What is interesting about fold points is we say nothing should be in the list twice. And we can write that as a lemma too. So if we've got any fold function and any list of points, then do I want to take that visited set as an argument? I think we'd better do so. So our lemma is, how do I say it's only in there once? Well, so it's easy to say the head is not a member of the tail, which applies only to the first argument. And then we could do that for everything. But what's the property look like? Because we can take a sublist, but that's not. Oh, okay. We can do count. Let me just check that. Yeah, okay. So the count should either be 0 or 1 for anything. So for all points P, I could put a type in if we needed to. Count of syntax. Count of P in fold points FFL visited is less than or equal to 1. All right, so I'm pretty sure we can't prove that automatically. Yeah, I didn't expect it. All right, so how can we prove this? So the obvious thing to try is induction on the list. But I'm not sure that gives us... okay, there's been something I'm meaning to try. I've been meaning to try... There are... Okay. Okay, we can use... All right, so to do this, we'd need a lemma. So why don't we just write our lemma right to begin with? So we'll take another argument, and all our arguments are essentially for all. We're saying this lemma we're proving is true for any values of the arguments we give. Okay. Well, so let's try this. So if usually the base case is fairly easy, I can get that. So if the list is empty, then fold points is also empty, and so this should be trivially true. All right, and it agrees. So if we could prove that the inductive step had the right value, then it can handle the base case and can handle the induction. So problem is, because of the way I wrote fold points, it may be difficult to do this. It's not clear that the inductive step helps us. We may need to refactor the function or prove something, prove that the function is equivalent to doing something else. So let's just think about the case where you got one element. All right. I'm not even sure how we're going to prove things about count. Do we have any lemmas about count that help? Member implies if and only if count is greater than 0. Okay. All right, so I think what we'd like to prove is that FF head is not a member of not appear, but that's not true. It's only true if we match the implementation. And so that seems like the sort of thing we have to prove as its own lemma. List. Yeah. Okay, so let's do that. So the folded points doesn't. Okay. Respects visited. So we're going to write the lemma, and this time we're going to say if we know that P is in visited, then P is not in L visited. Yeah, so what we're full points. All right, so we don't trivially have that, but this induction should be simple. I mean, it's almost obvious here. Okay. So if it's the empty set, it's not true. If it's true of a shorter list, then in this case, we know this is true because we put in the requireds. So it should be true of the longer list. So how do we write that? I think we just can give it as is. Is it fault? Oh, to make this recursive. Respect. No, it's not good enough. Okay, why not? So we think that All right. Was I think I know what I'm doing wrong. So I was sort of in my head I was saying, oh, this is what we've got, that folded points, the two lists are equal, and they're not equal. They're only equal uh if head is this point we care about, or rather, ff of head is the point we care about. So um, if let's divide up those cases. So if the head is, all right, now if okay, this was wrong anyway. All right, so in this case, this is true, and so we can just appeal to the inductive hypothesis. Otherwise, do we have to, what is it equal to? It's equal to that. And P is not, oh, and P is not equal to FFHD. Maybe this will work. Fold points. Okay, still not happy. We're missing something. Let's make sure the first case works. All right, so the problem is in our second case. All right, this says it's not in this list. All right, let's just write that out. What it says is, it says not, P is not a member of tail. You know, union, blah. All right, and so if it's not a member of that, then it should also be the case that it's not a member of the result, which is consing that first element back on. And that's where we might need some help to prove something about list member or appeal to an axiom. That might be what we're missing. Okay. Yeah, let's look at what we know about oh, there's this whole no repeats thing we should be using. All right. Well, I don't think that directly helps us. This helps if we're using a pen, but we're just using const. So that should more or less come free. Yeah. Hmm. Okay. Um, let me just check that we're still on the right track. Okay. So what do we know that it doesn't know yet? I mean, obviously it doesn't know our conclusion. So does it know that this is equal to that? That be should be obvious. We can ask. Okay. So we think that why is my line wrapping behaving so strangely? Huh. I think I screwed up my Emacs environment somehow. All right, we think that is equal to the thing we're trying to prove something about, which is L and visited. All right, so that's the problem is somehow it doesn't, somehow the definitions, I'm either screwing up the definition or it's not getting applied correctly. Right, so we think that we've proven we're in the case where uh, we think we're in the case. Okay, maybe this is the problem. So we think we're in the case where ff the function applied to this head is already in the set. All right, it does not agree. Why not? Oh no, we're in the case where. Oh, do we? I guess we have to handle both cases. All right. Yeah, that's the problem. Is we made this assumption, and that's only we didn't specify that nothing else is envisaged. Anything could be there. So it says, hey, this element could be there already. So I don't know. Either way. Okay, so we'll just handle it as an extra case in our proof. What's wrong here? Person. Okay. Okay, so this is the case where it's not true. All right, so we managed to prove that. I think we can comment out these other assertions now. Now that we know what's going on. All right. So we've proven that this function will never return a point that's in the visited set. And here we added a point to the visited set. So let new point equals okay, so we appeal to the lemma we just wrote. Folded points respect. Do we have to use a lemma up from set? this should work. So these lemmas have this extra line that you don't see on my lemmas called SMT PPAT, and that basically says whenever you see this pattern, introduce the lemma to the SMT solver. So we're asking for membership of union, we're asking for membership of singletons. They both should be there without us having to mention them, which we could do for this lemma as well, but that get kind of gross. Since we're only likely to use it once, there's not a lot of point writing the. Okay. Specs. What are we doing wrong? Oh, it requires a point. So head will first point will not be there again. So is that sufficient to prove? No, we didn't get lucky. Okay, so this says we proved above here that it's not a member in the tail of the list that we get back. And so what we need to show is that implies that the count on the whole list has to be less than or equal to 1. All right, so if P is that, then hopefully we're done. Otherwise, we can work on the rest of the list. Tail. D duplicate. Nope. Okay, let's see if I was right that it's usually the inductive case where the mistake is. Both cases are bad. Yeah, both cases are bad. All right. Maybe we have to prove something about how count behaves. Or it could be the problem that the same problem we had before is it doesn't know how the two cases in fold points behave. All right, let's try to at least, this one should be easy. All right. All right, can we say that that is true? Oops. Count P. Got the order Mr. All right, it doesn't believe that that follows from what we know. So our lemma isn't strong enough. It should be though. I mean, it's a matter of logic, but maybe you have to not member implies count 0. All right, so if you've got a list, and we know, and then I'll write this in general. We've got a list and we know phi is not in the list, then that should ensure the count of LV equals 0, right? That's what we believe should be the case. Oh, phooey. What's going on there is technical. We can't just use any type. We have to use types that have decidable equality. Count phi. All right, so that's a missing piece. So why doesn't it know that? Do we have to introduce? Okay, so this lemma, I think, is the one we need, and you see it doesn't have SMT pat, so it's not automatically introduced. So let us make use of it. So it's list list. Huh. They put the arguments backwards. List. Oh. Okay. So we prove that. List tote mem count. What's our list? Do we need the tail? Yeah. That's what we got. Wrong order. Doesn't know that yet. Okay. Still not enough. Okay. Okay, so we know this about this list and this list are not the same. So it's the same problem we had here, I think. So if I think we have to split it up by case, matching the function. This is often the case that the proof of a function's correctness matches the structure of the function. Okay, so if we visited it already, then we use our lemma to say it's not going to show up anyplace else. No. I'm getting confused. I should have come up with a better plan or been more organized about writing this. Okay, so I believe this case we use the inductive hypothesis. So if the first point is already in the set, then the function is of this, the return value is just of this form. So it's called with tail, and visit doesn't change. All right, so let's see if that case works. Okay, good. That's progress. All right. So otherwise, if P is that very first point, then we're going to say the rest of the all right, so we know that it's 0 in the rest of the set, which should be good enough to tell us that it's less than or equal to 1 in the current set, in the current lists, in the full list, I mean. So let's see if that flies. It does. Okay. So it can reason from, hey, the count's 0 to, well, it's got to be less than or equal to 1, even if we add 1 to it. So I'm glad that didn't require any. Okay, so now we've got, I think we just need to prove this true about okay, that worked. So in this case we used our inductive hypothesis with the set as is. In this case we used the inductive hypothesis uh, with the set updated. And both cases tell us it's true for all p. In this middle case, we handle the case where p is actually, the image of the fold in the first, sorry, where the point we're making the assertion about is the image of the first point in the list under the fold function. And for that, we just need to show, hey, we're going to add it to the set. We're never going to add it again. And the lemma we wrote does that. And then we know since it's not in the list, its count is 0 in the remainder of the list, and it can figure out, okay, that means it's less than 1 in the full thing. So our proof is not all that complicated once we know the parts to write. There's only a few lines here, but it is more complicated than the original function. But we successfully proved that the list we get from it is deduplicated, which is what we wanted to. But fortunately it was not a bug we made. So I'm gonna call the stream, end the stream. We did manage to prove. I think we did pretty good today, actually, at proving the correctness. We didn't do this. We didn't do this for the fold along y, but we could easily. And we proved that we deduplicate, which is important for part 1, but not actually important for part 2. If we didn't deduplicate, then part 2 would work anyway, because we're just printing out the coordinates, and if it's in the list twice, then that's no problem. So that's a little amusing that we don't actually need that correctness property to do part 2 of the problem today. All right. Well, thanks for sticking with me as I tried to do some fairly basic mathematical reasoning there. You can see why proving things about your programs is not a more popular activity. So I am traveling to California this week. So the stream may be delayed, but I do plan to do it as close to 9 p.m. Pacific, 12 Eastern as I can, but it'll be a different background behind me. So thanks, as always, to the organizers of Advent Code and to the sponsors, which includes my employer, Akita Software. And I will see you all later. Bye.